Evaluation metrics measure how good your model really is. Welcome back to my channel. Hope you all are doing good. Today we are going to discuss on the topic of evaluation metrics, which is required for your classification algorithms. And we will start with the topic. But before moving ahead, while subscribing, guys, one important note: please hit the bell icon so that you will not miss the latest updates. So let's start with the topic. So let's start with our topic. So what is a metric before moving ahead? A metric is the one by which we can measure, or that's a fundamental measuring tool to evaluate any performance. Similarly, for these algorithms, how your machine is predicting, we need to understand that, right? And for measuring that, we have different evaluation metrics. So here I am going to cover on all the evaluation metrics which are responsible for comparing with different classification models, or understanding how the model predicted. So all those things it is going to understand, or it is going to tell you that the evaluation metrics. So let's start. So first one is going to be a confusion metrics. So this is a very important aspect, because when you're talking about classification, here number of classes, the target variable, it's not a continuous variable, it's a categorical variable, and number of classes are going to be involved. It can be binary or it can be multi-class. So to handle that, they have designed, like the scientists have designed in such a way that these metrics will be helpful in determining, or these are the statistical tools which can be helpful in determining the worthiness of the model, how it has predicted. So when you're going ahead with the confusion matrix, again it's a table. It's a table where we have, or it contains true positives, true negatives, false positives and false negatives, and it is helpful to evaluate the performance of a classification model. And basically, what we are trying to understand? We are trying to understand the actual predicted values, right? Actual predicted values. And for that, we need to know how many true positives, true negatives, false positives and false negatives are associated to achieve that. So for that, this is the one how it is getting presented. If I'm maximizing this image, so you can see that this is your false positive, right? This is a true positive, this is your false negative, this is a true negative. So it's based on this kind of quadratic presentation, guys. If you like, we have already gone through the coordinate geometries, right? So in coordinate geometry, right, straight line is not straight line, not looking like a straight line. Let me draw a straight line. Yeah. So coordinate geometry, what we understood, we have plus, right? Then how our measurements are. This is how your measurements are, right? This is 0, 1, 2, 3, 4, 5. Similarly on this side, -1, -2, -3, -4, like that. This side, 1, 2, 3, 4, 5. Similarly here, -1, -2. So if we derive this in 4 coordinates or 4 planes, which are talking about, or quadrants, how it is, right? This is plus, this is minus, plus. This is plus, minus. So not this plus, minus. This is minus, minus. This is plus, minus. So this, if we resembling this with these fundamentals, it applies the same, like it is dividing the whole output into 4 quadrants, and based on the output, or like how your actual predicted and your actual value, my bad, actual value and predicted value, how they are getting counted. It is going to divide it into 4 quadrants and it is going to tell you that. So what is, let's understand what is a false positive, true positive first, because this is the first one, this is the first. So true positive is nothing but the model, how your model correctly predicted the positive output. So when we are talking about true positive, what is that? True positive is nothing but how your model correctly predicted a positive class. Again, what is a positive class? What is a negative class? Suppose consider a binary classifier problem. In that, if you are detecting or if you are determining a spam or not spam. So spam here is a positive class, not spam is your negative class, right? So here, in case of true positive, it's the model's worthiness on how it is correctly predicting the spam class correctly. Then true negative means how your model is predicting the not spam class correctly. Similarly, false positive means the model incorrectly predicted a positive class. So it's called a type 1 error. Type 1 error. Very important and mostly asked interview questions. These questions are a must in your interview. So false positive means when a model, right, incorrectly predicting a positive class. When a model is predicting, it's actually a negative class. However, it is telling that it's a positive class. So it's a falsely telling that. Or maybe based on your intuition or biasness, there is no generalization in model. That's why it is doing that. Then false negative, that means the model is incorrectly predicting a negative class. That means it's a type 2 error. So this is how your confusion matrix is getting presented. Just remember this, quadrants. False positive on this side, true positive, false negative, true negative, right? So let's understand the example, like whatever we understood there. I'm going to show you how in real scenario or how on the back end that's happening. So this is one example which I have taken where a patient has a disease and we are predicting for the future set of patients and these are the values actual and predicted whether the patient has disease or not. So when we are talking about disease, that's a positive or positive class. When we are telling that the patient has no disease, that means that's a negative class. So here, this is a data set for 20 patients I have taken. So these are the different counts: actual, predicted, positive, negative. Everything it has taken, it has recorded. Now, what is the first step here we have to do? We have to identify the true positive class, true negative class, false positive class, and false negative class. Just to remind you, this is how your quadrants look like. This is false positive, true positive, false negative, true negative, right? Just remember this table. This is going to be your life. This is your false positive. Okay. True positive. Yeah. Now, we will see how we are calculating. So, when we are talking of true positive, that means whatever the predicted positives and actual positives present in this data set, it is calculating that. So, it is adding everything or adding the count. So, in this data set, we have the predicted positive and actual positive. These are the numbers 1, 2, 4, 5, 11, 15, 17 and 19. 1, 2. That means both are positive. Not one should be positive and one should be negative. In that case, it won't consider. True positive means all, like in both actual and predicted, both should be positive. So, it has identified that and it has noted it down. So, I am getting count as 8. Then the true negative. predicted negative and actually negative. That means both should be negative. So if you see, if just to verify, 6, 7, yeah, it's true. 9, yeah, both negative are there. 10, both negative are there. Then 13, we both have negatives. 14, negatives are there. 16, 18. So we are correct. So it's just count. This is the count, right? This is the count. Then false positive. This is one of the trickiest part, how we are calculating. We are calculating predicted positive and actual negative. Predicted positive and actual negative. What is the meaning of that, or how we are inferring it? That means the model actually or the model predicted positive output, however that is actually negative. That's what we understood, right? Model, but however that should be negative, but it has predicted positive, the output. So how many counts are there like that? So we have 2 counts. That means these are the errors, guys. Just remember this. This false positive and false negatives are your type 1 and type 2 errors. So here I am telling that, okay, I have 2 errors present in both. And what is my false negative? Predicted negative and actually positive. So this is how your confusion matrix table looks like. So actual or predicted, positive, negative, positive, negative. So positive is coming like this, negative is like this. Like first true positive, right? True positive is 8, then false positive, then true negative, false negative and true negative. This is how the representation is like, looks like. First true positive, then false positive, then false negative, then true negative. Just like this. First this two, then these two. Right? Now we will go ahead. And in confusion matrix, where and how it's getting used and what are the important factors where we are considering, and in which cases it is more beneficiary and which cases it is not. So first, it is handling the error, right? So when we're talking about identifying specific errors, it is helpful to do that. Then when we are calculating different like when you're calculating different metrics such as accuracy, precision, recall, F1 score, balancing error, multi-class classification, all these are the integral part of your confusion matrix. And what are those things? We will explore that. But in short, we will understand what exactly is accuracy. Accuracy is the overall correctness. Accuracy is a term where we are telling how better your model has predicted till now. So that's your overall correctness. What is precision? Precision is all positive predictions. In whatever the positive predictions your model did, how many were correct in that? So that's your precision. When I telling precision, right? That's the meaning of that. So what is recall? Recall is your actual, like whatever the actual positive cases are there, how many did the model correctly identify, right? So precision is whatever the total positive predictions, how many were correct. Recall is the actual positive cases, because there is type 1 and type 2 error also present, right? Whatever the actually predicted positive cases are there, it is going to correctly identify how many are correct from that. The F1 score again is the harmonic mean of precision and recall, or you can say that it's a mean of precision and recall, and very useful for imbalanced data. For imbalanced data, we are preferring F1 score over accuracy. Then what is a balancing error? Balancing errors is a concept with which we are understanding by balancing different types of errors. And it is very helpful in determining or the criticality of applications like fraud detection or any kind of disease diagnosis you are performing. So in those cases, it is very helpful. Then all these things can be useful for multi-class classifications as well, like where you are extending more than 2 classes. These things are very helpful in that case as well. So that's what your confusion matrix concept, guys. Now let's move ahead and see how, like, this is the confusion matrix table. Out of that, those true positive and false positive, those metrics, how we are going to play with that, and how we are going to understand the different aspects of those four metrics, and like we are formulating with different points. So the first point here is the accuracy. So what is accuracy? Accuracy again is a part of confusion matrix, where we are telling that all classifications that were correct, we are telling that what is the portion of all the classifications that were correct. Like here, how we are calculating that? We are calculating by summing the true positives and true negatives by total number of predictions. So in short, this is the formula: true positive plus true negative divided by the total number of predictions. That means it is going to contain true positive, true negative, false positive, and false negative. So in short, the accuracy measures the number of correct classifications it did in the model by total number of cases. So most of the times it can be misleading in case of imbalanced data. What is the imbalanced data, guys? Suppose you are considering like you are taking a target variable, and in that target variable you have two classes. Suppose two classes, true or false, or yes or no. So in that cases, if you will consider the yes part as 70 and the no part as 30, that is imbalanced data. You should always consider the true part as 50 count, false part as 50 count if your total data set is 100. So that's how your balancing of different classes in your target variable looks like. So this is highly, or this is not recommended. Accuracy is not recommended in case of your imbalanced data sets kind of thing. So that's how we are deriving our formula, and whatever we have seen the example on top on this one, this is how we can calculate it. So we understood our true positive. We have calculated our true positive from this data set which we have taken in an example. Then we have calculated true negative there, and we are adding up all. So we are getting the score of 0.8 for the above case. And here in this case, guys, the output which we are seeing is a balanced data set. That's why we are getting better scores in everything. But let's see and explore. I have taken one more example where I am showing imbalanced data set and how we are calculating that. So here we have different kind of limitations at the same time for accuracy. When you are considering any kind of anything, we have pros and cons, we have limitations as well, because nothing is perfect in this world. So here similarly we have few limitations, and one I have already told about in our previous slide, that it is not working good with imbalanced data. For imbalanced data, I think F1 score is the better choice as compared to accuracy. And suppose, take one example, when you are working with a data set where one class is outweighs another, or the one like I have given one example where yes or no, the yes class is containing 80 rows or the 80 data points, and no class is containing 20 data points. That means biasness will come into picture, and with that the model will definitely going to predict whatever the upcoming predictions will happen. It is going to tell, okay, all are yes only. So with this accuracy, we can differentiate the types of errors through your confusion matrix, right? And with those type of errors, such as like false positive and false negative, which we are talking about as type 1 and type 2 errors, we can explore the model's limitations, the model's capabilities. Then we will understand on your precision. What is a precision, guys? Precision again is a concept, or is a part of confusion matrix which helps on understanding or on measuring on how many positive predictions made by the model were actually correct. So the total number of positive predictions, whatever you have or the model has done, we will see with this precision how many are correct, how many it has correctly predicted. Then how we are calculating this? We are calculating by total number of true positives, because in true positives we are adding up both actual and predicted positives, right? So true positive divided by the true positive plus false positive, or the predictive results, right? So this is how your formula looks like, and these formulas you have to remember, guys. You should not miss these formulas. So what about your total number of positive results or positive predictions? That's nothing but a true positive plus false positive, because you are adding the errors part as well there, right? So this is how we are calculating from the above example. Whatever the example we have taken on the top side or the top section for confusion matrix, this is what my precision looks like, or the output. Then when you're talking about high precision score, that means the model predicts a positive case, right? And it is very likely it's correct. And what it does, it indicates the low rate of false positives. That means if you are getting, suppose in this example, we are getting 0.8. So 0.8 is saying that 80% of my output or 80% of my prediction in the total number of predicted output is correct. It's a positive, which is a good score. That means the 20% can be your false positive, and it's a low rate again, right, at the same time. So that's what it tells. Then in case of low precision score, it is telling that high number of false positives are present in the model. That means whatever the predictions it has done, most of them are not correct. That means then this precision is very beneficial or very crucial when the cost of false positive is very high. Like there are very sensitive models when in most of the cases where understanding or where getting more false positives is really very uh, it, like, people have to pay a more cost for that. They cannot take any chance of getting, or the sensitivity of the output shoot is very what I can say, very undetermined. In that case, they, like, these kind of precision study is very important. Suppose in case of spam detection system, where misclassifying an important email as a spam is very problematic, right? Because suppose you are getting a job call letter in your email, and think that if the model or if the AI is predicting that as a spam, and it is going to send you the spam folder, and you are waiting for days to get the letter. I have not received the letter, and when you're calling to the to your HR, then they are saying that we have already sent it. Then how it looks like? It's a very problematic situation for a future, right? So in these cases, it is very important to understand how your model predicted, what is the percentage of correctness in the prediction. Then we will understand about recall. So recall is again called as a sensitivity or the true positive rate, and it is a part of confusion matrix. And what it is happening? It is understanding the model's ability to correctly identify all the instances within the data set. That means in the scenarios, or in this case, we are understanding how we can minimize the false negatives. We are minimizing the false negatives. That means, what is the formula? What it could be, right? It's true positive divided by true positive plus false negative. That means whatever I have or my model has identified, I am understanding how many percentage of false negative is there, and by getting the recall score, I am understanding, okay, like whether it's less or not. My false negative part is less or not. So there are two concepts. One is sensitivity and one is specificity. Specificity is, getting the true negative rate. Recall or sensitivity is to get the true positive rate. That is two difference, sensitivity and specificity. So when we're talking about high recall, that means what it is saying or what it indicates that your model is good at identifying most of the positive cases. That means your false negative is less, right? And in case of low recall, that means your model is missing positive cases, and there is a lot of serious consequences when it is coming to the output, right? So that's your recall. Then we have F1 score. F1 score, again, it's like it's a formulation of your combining recall and precision, and it is very helpful in case imbalanced data set where accuracy is going to mislead, right? And when I'm talking about F1 score, it combines both precision and recall into one metric. And when I'm talking about regression cases, because not regression cases, my bad, when I'm talking about the binary classification cases, in that case, it's just we are taking the mean of that. That means when I'm talking about binary classification, we will just take the recall plus precision divided by 2. That's how your F1 score would be. And in case of multi-class, or where the biasness or the imbalance data is more, right? Or like when you're seeing that one class is more having more weightage than the other classes, in that case F1 score is better. And this is what the formula looks like. Okay, 2 into recall into precision divided by recall plus precision. 2 into recall into precision divided by recall plus precision. So what is my recall, guys? Recall is true positive rate. Recall is again called as sensitivity. What is specificity? True negative rate. And from the above example which you have seen, I am connecting the dots with the above example. So we got this score 0.8. So in this F1 score, this is the one kind of metric where it considers both false positive and false negative. So none of the things are ignored in this, right? Because in recall and precision, both have false positive and false negative as a part in that, right? Now we will understand. So now we've covered all the important metric and mostly asked interview questions, guys. Must question. You will get a must question from this. And we will see. We have seen one case with balanced data. Now we will see one case with imbalanced data. So in a fraud detection data set, we have 100 rows. Okay. In that 100 rows, suppose take one case where you have 95 non-fraud case and 5 fraud case. So when we're talking about non-fraud, we are categorizing that as 0. And when we're talking about 4 fraud case, that we are categorizing that as 1. So out of that, I am saying that I have my true positive, or whatever the calculation or the count which I got from the data set. I have taken a summary. So I am getting 1 frauds correctly predicted, true positive. That means true negative, I am telling the non-fraud correctly predicted 94. True false positive, non-fraud predicted as fraud is 1. Then false negative, fraud predicted as non-fraud 4. And this is how my confusion matrix look like, right? Then, and this is my accuracy score I got. 0.91. So when we're seeing this data set, even though it is imbalanced data, I'm getting accuracy score is 95%, which is really misleading because my model is going to miss most of the fraud cases in this, right? So, and this is what my precision I got, 50%, it is telling that only 50% of predicted frauds are actually frauds from this model. Then recall, I'm telling that my model detects only 20% of actual frauds. That means it is a very poor case, right? F1 score I got 95% accuracy and not my bad. F1 score I'm getting 0.29. That means very low F1 score despite of your 95% accuracy. That means your accuracy fails for your imbalanced data set. This is how I have proved that your accuracy fails. So in case of imbalanced data, you can consider F1 score. So we have completed our discussion on confusion metrics, accuracy, precision, recall, and F1 score. We will understand few more metrics which we have or which are responsible for your classification algorithms. We will see that. So till the next time, bye. Well, that is all for now. We will cover the further evaluation metrics, whatever the left out part of evaluation metrics in our upcoming next video. Then if you really like the content, guys, please go ahead and subscribe. While subscribing, do not forget to hit the bell icon so that you will not miss the latest updates. Like, share your comments, share your valuable feedback. That's really helping me to improve my performance day by day to make the contents. And see you till next time. Bye. Take care.